I'd like to now talk about sigma notation, which was part of the notation used when I was referring to the Riemann sums in the previous examples. So sigma notation helps to write more concisely a summation of many terms. Okay, so that's what it is. It's a concise notation for a summation of many terms. The way to think about it. So I'll start with an example, maybe something like this. Summation of I equals 1 to, I'll just take 3. I don't want to make the problem too large for this example. And I'll take I squared plus 3i plus 4, and I will just evaluate this directly. So directly means that I just write out the terms, okay? So here's my counter, right? It's going to count. So it's also called the index, right? I sometimes call it a counter because what's happening is as you start to write out the terms here, this I value will count from 1 to 3, basically. So right now I know there's going to be 3 terms because there are 3 numbers from 1 to 3, the numbers 1, 2, and 3. So this tells you the beginning of the index, and this tells you the end of the index. So I here will be 1 in the first term. So I would have 1 squared plus 3 times 1 plus 4. Okay? That is term number 1 in this expression. Okay? So 1 goes in for I, and now I have that term. Now there's supposed to be 2 more terms. So terms means I'm adding. So the summation now tells me I'm adding, right, the second term. The second term will be the exact same expression, but now I will be the value 2 instead of 1. Okay? And we'll end with 3. So 2 squared plus 3 times 2 plus 4. Plus the third term, right, which is the last term in this case, at the end of the counter here. So we will have same expression with 3 plugged in, 3 squared plus 3 times 3 plus 4. All right? So we can compute all that and tell what the sum of all of these terms is. And that will be 4, 7, 8. So 8 plus 4, 6, 4, 14 plus 9, 9, 4. So 22. All right. 30, 44, looks like 44. Oops, should be equals. Equals 44. Okay, so there's the answer to that particular summation using sigma notation and writing out directly what we had. Now there's another way to approach it, which is the usual way, because a lot of times you don't go from 1 to 3, you go from 1 to a much larger value. Okay? So the sigma notation has a lot of properties, and one of them, right, as you could probably kind of tell here maybe, if you were to rearrange these terms within here, you could write this in a little different manner. So I'm going to do that very quickly here, hopefully. So this 44 value, all this is really the same as, I could rearrange all of this. I'm going to remove the brackets, and it'll help to clear up why the summation notation, the sigma notation has these particular properties probably. And then we'll write out the properties in general in a moment. So if I remove the parentheses, we would have 1 squared. I'm going to group the 1 squared with the 2 squared and 3 squared, right? Because it's all just adding. At the end of the day, it's all adding. So 1 squared plus 2 squared plus 3 squared. I could do that. That takes the first term from each of these 3 larger terms. And then I could take the 3 times 1, 3 times 2, and 3 times 3 together. 3 times 1 plus 3 times 2 plus 3 times 3. and then I could take that last value of 4 and have 4 plus 4 plus 4. Okay, so now if I view it like this instead, just for a moment, I'm just rearranging everything to illustrate why this notation should have the particular properties I'm going to exhibit in a moment. So this expression here, right, should be nothing other than the sum of a quantity squared as that quantity goes from 1 to 3. Okay. This one, if I factor the 3 to the outside, right, I have 3. I have nothing but 1 plus 2 plus 3. So that would be a quantity changing, right, from 1 to 2 to 3 and being added together. That would be exactly this notation. And the last one, if I factor out 4, if I factored 4 out, I'd have 1 plus 1 plus 1. So that would be nothing other than 1 added to itself 3 times. C doesn't depend on I. There's just a value in here, right? And a lot of times, instead of writing a 1 in here, it will be actually left blank. So one of the properties we already noticed, just by rearranging terms and rewriting back with the sigma notation, we can see it has a sort of distributive property. Right? You see that the sigma notation moved into the parentheses and applied itself to each of these 3 terms separately. Right? And not only that, but constant multiples could be factored to the outside.